problem 8.2.15. So the question is that remember that when we do the least squares approximation of functions using polynomials, we'll see the normal equation which looks like this thing for each row. Okay, so essentially you have this Hilbert matrix which is composed of this kind of unit rows in that matrix. This AKs will be the unknowns we try to solve for, and this is the right hand side. The question is, can we show that this normal equation has a unique solution? Basically means that if this is a linear system, which we have this Hilbert matrix formed by those kind of things, and then the right hand side, so then we have the A0 to AN, and on the right hand side we have this on each of those terms on the right hand side for k equals to it should be k equals to from 0 to n. So if we want to show that this linear system has only one unique solution, we just need to show that this one is non-singular, right? Or in other words, we can show that if this times this thing equals to 0, then this thing has to be equal to 0. Okay, if we can show that, then this shows that h is invertible. It's non-singular. So in this case, this equation must have a single unique solution. Okay, so remember again, how do we show that this one has a unique solution? It's just to show that if this side is completely 0, then this has to be equal to 0. Then this just means that H is invertible matrix, right? That's what we learned from linear algebra. Okay, so how do we prove this? Again, as we said, we just set the right hand side to 0. And if the right hand side is 0, then you can see that here it will be just equal to 0. So it doesn't matter what you multiplied. This whole right hand side will be just a 0 vector. Okay, and then you look at the left hand side. Okay, so because this is equal to 0, on the other side, we can multiply this with the aj. So we can multiply this by aj, and then this side also by aj. But it's multiplying aj to 0 on the right hand side, so it's always equal to 0. But on the left hand side, this one multiplied by aj will become this. Now you can see that because this is the integral, so you can put this sum into that. Then when you put it there, then we'll have these terms coming out. Okay, so now you can also put this together with that. So that just means that we have an inner product of ajx to the power j with the sum of these guys. So it's aj to the power x power j and the sum of the things. Now, because this is always equal to 0, so that means if I make a linear combination, so this is true for all the j's. Okay, so I can make a linear combination of these aj's. So for j from 0 to n, then we'll actually have, essentially I'm just multiplying this thing with each term in the sum. Okay, so because this is like the j's term of this summation. So if I take the j from 1, so I have the j from 1 to 0 to n, then we'll get this, because this is always equal to 0. Every term of this equals 0. Take the sum, is still 0. So that's giving us this. But now, look at these two terms. They're exactly the same, except that the j, I changed the notation from j to k right here. Okay, so essentially they're the same term. So we call this px. We call this term px. Both are just px, which is I defined it here as the px. So it's essentially just the inner product of px with itself. Now, the inner product of px with itself is defined to be this, and this is equal to 0. So this is equal to 0 means that this px has to be a constant 0. It's a constant function, which is taking the value of 0 all the time. But the p is a polynomial, on the other hand. So what kind of polynomial can be always equal to 0? And it has to be just a 0 function. Okay, so that's why the px has to be equal to the 0 function. And this means that these coefficients, which are these coefficients in this p polynomial, will be always equal to 0. So this shows that if this side is 0, then the only solution to this system is that this one equals 0. And this means that H is invertible matrix. And this means that for any arbitrary right-hand side you have here, you will have a unique solution, A0 through AN, because this H is invertible matrix.